thank you for the introduction, and thank you to the organizers for the invitation to speak here. I spoke about this topic actually last month as well in Mexico, so I'm really sorry if this is your second time listening to me talk about it, but hopefully I managed to confuse you very much last time, and this is not going to be a total waste of time this time. Okay, so let me set up some notation. P will be a prime bigger than 5. Some of what I say can be done for P equals 5, but to go lower than that, you really have to change the tactic a little bit. Okay. F will be a totally real finite extension of Q. With P inert, and this can work. All of this can work with P unramified, but for simplicity, I'll assume that P is inert. And V will be the place of F dividing P. Okay. OF will be the ring of integers of F. GFV will be the decomposition group of F at V. And for our coefficients, O will be the ring of integers in some large finite extension of QP. Okay, so we'll be working with the Hilbert modular scheme defined over O. So this is going to be actually smooth of hyperspecial level at P. So Hilbert modular scheme. Of some prime to P level, some small prime to P level. And this is the Shimura variety for the Weyl restriction of scalars of GL2 from F to Q. And roughly, although this is not literally true, but roughly it parameterizes the moduli, the following moduli problems: some abelian scheme over S of relative dimension equal to the dimension of F over Q. A ring map from OF to the endomorphisms of this abelian scheme over S. And some additional data. And we look at the isomorphism classes of this data. And in particular, it generalizes the modular curve when F equals Q. And because there's this abelian scheme living over X, which is, well, again, not literally true, but almost true, the universal abelian scheme and in the identity section, you can define a sheaf omega as the push forward of the sheaf of differentials of A over X, which is the same as the pullback along the identity section of this sheaf. And this is locally free of rank 1 over the ring OF tensor the structure sheaf of X. And this OF action comes from the action of OF on the abelian scheme. But this, because we chose O to be sufficiently large, this breaks up as this breaks up over the embeddings of F into QP bar, or yeah, F into QP bar. Right, and this will be a line bundle now living on X. Okay. All right. So this is the setup we are working with. And we'll choose integers maybe I'll write here. So I'll choose integers k, a tuple of integers k, indexed by these same embeddings, tau from f into qp bar, that are positive integers and of degree equal to the degree of f over q. Okay, so by a mod p Hilbert modular form, of weight k, I mean an element of the degree 0 cohomology of, so we look at the special fiber of this thing, maybe just take the algebraic closure if you like, and take the tensor of all of these line bundles raised to the power k tau, where k tau is part of the data of k. Technically, I should take some compactification of this scheme, but by Kocher's principle, it does not matter in the case f is not equal to q, which will be the only case of interest for us in this talk. And I'll say why in a bit. But so I'll ignore issues. There are no issues with compactification, and I can just work with the uncompactified Hilbert modular scheme variety. Okay, so on this, there's an action of the prime to p Hecke algebra. I should also say that I can twist this line bundle by another line bundle, which is non-canonically isomorphic to the structure sheaf. And that changes the Hecke eigenvalues that can show up. And then I should say a little bit more about what the weight would be, but I'll basically ignore that twisting completely because it would just complicate notation and it won't help with any of the points. Okay, so this is the sheaf we are working with. Okay, we will say that our weight k is regular if each of these k taus is bigger than 1. And we'll say it's irregular or alternately partial weight 1. So k tau is 1 for all, greater than 1 for all tau. And if k tau is equal to 1 for some tau. Right, so if one of these is 1, then it's irregular. And in the modular curve case, these would exactly be the ones that do not lift to characteristic 0, and these would be the ones that do lift to characteristic 0 in coherent cohomology of the Hilbert modular scheme overall in the modular curve case. Okay, so right, so if I start with a Hecke eigenform, let me call this mk. So if I start with a Hecke eigenform for this prime to p Hecke algebra, then there's a way to associate to this Hecke eigenform a mod p Galois representation, which is from the Galois group of this totally real field to GL2 FP bar, such that at unramified places away from P, the Frobenius characteristic polynomial matches with the Hecke eigenvalues, such that in some way, in some particular standard way. So characteristic polynomial of Frobenius corresponds to the Hecke eigenvalues. And this association has been given by a number of authors, but most generally due to Diamond and Sasaki, but also due to, before that, due to Emerton-Gee Shao and Goldring-Koski-Verta. Okay, so now let me say what I mean by local global compatibility. By mod P, local global compatibility, which will be denoted LGC. And remember that we are working on the Hilbert modular variety. You can frame it over whichever quaternionic Shimura variety you're working with. We mean that if rho bar, again, so the absolute Galois group of F into GL2 FP bar. So if this is irreducible, continuous, and totally odd, and associated to a Hecke eigenform, rho bar equals rho bar F for some Hecke eigenform in MK, then the restriction to the decomposition group at P, it admits a crystalline lift of type K, by which I mean of Hodge-Tate weights governed by K. So the Hodge-Tate weights are given by 0 and minus k tau plus 1, depending on whatever your convention is, in tau with embedding. And remember I said something about twisting that sheaf omega tau to the k tau with some thing non-canonically isomorphic to the line bundle. That would basically shift both of these weights by some fixed distance, but keep the but the difference between them will be governed only by k tau. I said I would not say anything about that twisting sheaf earlier, and I just did, but I will not say anything about it again. Okay. All right, so there's another way to state this. Equivalently, our representation rho bar G FV, this is a point of a certain moduli stack of xk, denoted xk, which is a moduli stack of mod P representations with crystalline lifts of type K. So maybe I should say a little bit about what this stack is. This is a closed substack of the Emerton-Gee stack, which is literally a stack of phi gamma modules, and it lives over spoof of O. Right, so xk is a closed substack of the reduced part of the Emerton-Gee stack. So this is the Emerton-Gee stack, which is a stack of étale phi gamma modules. For suitable coefficients, namely complete Noetherian local with finite residue field, étale phi gamma modules are the same as Galois representations, p-adic or mod P. So when we take the reduced part, it's now defined over the residue of O, and it can be viewed as a roughly parameterizes mod P Galois representations with appropriate deformation theory. And this is the closure of mod P reps admitting crystalline lifts of type K. Right, so once again, all that the statement of local global compatibility is saying is that you start with an eigenform of weight k, and then it's a point of this moduli stack xk. Okay, great. So Sorry, what time did I start again?
Started at, let's see, so started at 3:20, and that's 3 minutes now.
Okay, thank you. Sorry. All right, so there is a conjecture of Diamond and Sasaki which says that local global compatibility in this sense holds if the weights are in a certain cone. So you want pk tau to be bigger than equal to k of Frobenius inverse composed tau. So remember that tau is an embedding of f into qp bar, and there's a Frobenius, and it's unramified at p. So Frobenius will act on this set of embeddings, and this sort of relation is an analog of the minimal weight of a Hecke eigenform, it turns out. And so they say that local global compatibility is expected to hold in this cone, and it will not hold arbitrarily outside of this cone. Like, there are counterexamples to this kind of statement holding true outside of this cone. Right.
So can I ask a very, very naive question? Which
Yes.
I apologize if I missed an explanation you give orally. Why is this called local global compatibility?
That's a great question. So the Shimura data, I mean, I guess I could be wrong, but the Shimura datum is some global data, and the weight of the modular form is something global, and you associate to a global representation. But then when you're restricting it to local piece, you can exactly see the global data it corresponds to, or it should also mirror some kind of statement on a p-adic deformation ring in a Hecke algebra corresponding to each other.
Oh, thanks, that helps.
Yeah.
All right. So is the inverse expected to be true, like if I have the
That's a wonderful question. So that would be a much stronger local global compatibility statement. And I was going to say something about it in a bit, but maybe I'll say that one important significance of a statement like a strong local global compatibility statement would be applications to Kalyani-Garrity's approach to modularity lifting. But as it is, it cannot be directly applied. But maybe if one were to strengthen it, hopefully, in the near future, then one could actually apply it to modularity lifting, right? So the converse would be a part of strengthening of this local global compatibility statement. Okay. Okay, so in this talk, we will consider weights k such that each k tau is between 1 and p plus 1. And this is, so based on how I defined a crystalline lift of type k, this is basically saying that the differences in Hodge state weights are bounded by p, which is why even though it's actually not bounded by p, it is going to be called p-bounded. So and hopefully I'll say a bit more about why you really need the p-bounded condition. Okay. All right, so let me state our expected theorem 1, which is our main theorem. That local global compatibility for regular p-bounded weights implies local global compatibility for irregular or partial weight 1 p-bounded weights. Right. So once again, regular means the weight has to be bigger than 1. So this is k tau is in 2 and p plus 1 for each tau. And this is k tau in 1, to p plus 1 for each tau. Right, and once again, I want to emphasize, because this will be a little bit of a point later on, that this is, of course, local global compatibility for modular forms living on the Hilbert modular scheme. And this is also local global compatibility for modular forms living on the Hilbert modular scheme. The reason I emphasize this is because we'll actually consider some other quaternionic Shimura varieties in a bit. And I want to emphasize that we're only assuming it for Hilbert modular schemes to prove something for Hilbert modular schemes. OK, so let me make some remarks about the hypothesis. Actually, let me call this hypothesis chalk. So let me call this hypothesis star. So I want to make a few comments about star. OK, so remarks. One, when k tau is in 3 to p plus 1 range, so just outside of that lower edge, for each tau, then Deding-Yang has, one can use Deding-Yang's results on ampleness of line bundles and combine it with cohomology vanishing theorems like NO and Wieweg's theorem to show that star is true. And in fact, similarly, you can use Deding's results and Deligne-Elusi to prove a version of local global compatibility in some generic weight range for all quaternionic Shimura varieties. But this is in particular, this range will in particular be the range that it's true for Hilbert modular variety. Okay, secondly, when f is a quadratic extension of Q, then this holds by one of the results in the thesis of Siqi Yang, who is in this audience. In particular, she proves something much more general, but its application to local global compatibility is to these regular p-bounded weights in this case that f is a quadratic extension of Q. We believe that when f, degree of f over Q is general, so bigger than 2, this is approachable. And essentially, the point is that the difficulty in going from 3 to weight 2 is in some sense very related to the difficulty in going from 2 to 1. So you don't have lifting to characteristic 0 that Deding-Yang's results along with Deligne-Elusi or NO Wieweg give you. And somehow you have to deal with the case that you're not lifting to characteristic 0, where you have a lot more tools available. All right. So right, so I guess the key point is that it's not, in some sense, a very conjectural theorem. Like the hypothesis is very, very reasonable and hopefully approachable.
I have a question.
Yeah.
But the right-hand side is a bit outside the range of the conjecture of Diamond Sasaki.
That's correct.
So you kind of expect it holds a bit more generally.
Yes.
Yes. So maybe not out in the wide world, but some optimization can be done. Yes. Okay. I should also say that before this and recent work of Hanneke-Wiersema, which I'll talk a bit more about later, well, depending on how time goes, but let's see. What was already known was the parallel weight 1 case. So if k tau is 1 for all tau, that's a parallel weight 1 case. So in this case, our statement of local global compatibility, LGC, says that the restriction of rho bar to the decomposition group at V is unramified. And this was proven by, in varying degrees of generality, by Caligari-Geraghty, Emerton-Gee, and Shao, which I'll maybe just write as ERX because I've already written the names there. And Dimitrov and Weiss. And so we are working with degree 0 modular forms, and there is C-Ing Lee has work which works with H1 in the parallel weight 1 case. So that's some other very interesting work in this case. So again, in the parallel weight 1 case. All right. So I should say that when F equals Q, this basically settles the theorem because there is no partial weight 1 other than parallel weight 1. There's just one embedding. And so we'll basically not talk about the F equals Q case at all, in part because this settles in, and in part because our strategy simply cannot work in that setting. And it doesn't, so, right, so degree of F is at least 2 over Q for us. And again, if I have time, I'll say something about why a strategy cannot work. All right, so proof strategy. Any questions so far? Okay, so proof strategy. This basically involves two a priori independent steps. So step 1 is to, okay, actually let me make some assumptions. So now, forevermore, K will be irregular, P bounded, M will be a maximal ideal of the prime to P Hecke algebra, giving a Hecke eigensystem. For some eigenform F in Mk, and rho bar restricted to the decomposition group at V will be the associated local Galois representation, will be the associated rep. Okay. So step 1 is that if M appears in Mk, meaning the localization at this maximal ideal is non-zero, then there exists some set of weights Ki indexed by some set I, finite set I, of regular weights for some I of cardinality at least 2, some I such that I is bigger than 1, right? Such that our local Galois representation, it lives in the moduli stack of mod P representations admitting crystalline lifts of weight Ki, which is regular now for each I. So all we are saying is we start with an irregular weight modular form, but in fact you can see it in various regular weights as well. And you can see it in more than one regular weight. So that's step 1 of the proof, which of course I'll spend a lot of time talking about in a bit. But step 2 is then to show that if you look at the intersection of all of these loci, and you look at their FP bar points, then this intersection over over the set of regular weights, this is contained in the irregular locus. Right? And this would basically prove, so step 1 plus step 2 implies local global compatibility for weight k. Right, so in the first step, we exhibit our Hecke eigensystem in certain regular weight modular forms. And in the second step, we take the intersection of all of these regular weight modular, regular weight spaces of crystalline, mod P representations with crystalline lifts of these regular weights. And we demonstrate that the intersection must lie in the irregular weight locus. And then that would basically show that our rho bar actually lives in this locus because it lives in this locus. And so we're done, right? So that would be the proof strategy. Any questions about the strategy or the overall framework? Okay, so now let me spend hopefully a lot of time talking about step 1 and then maybe some time talking about step 2. I should actually say that step 2 is in some sense the bulk of our computations, but it's maybe not as pleasant as step 1. Well, I guess if you don't want to do combinatorics, it's not as pleasant. Okay. All right, so step 1. All right, so for step 1, right, maybe I'll say one more thing. Notice that step 2 is a purely local statement on the spectral side. And step 1 is so far whatever, something global, something else, something. Okay, so, right, so a possible strategy for step 1 is the following. So we do something called weight shifting. Which is, we find Hecke equivariant maps from mk to mki. Honestly, this will be with the twist. This really is the last time I mentioned the twist, so maybe there should be a prime here, but I'll omit the prime. This is not strictly true. It's almost true. Okay, so such that f goes to, and these ki are some regular weight, such that f, let's say this is phi, such that f goes to phi f, which is not equal to 0. And because these are Hecke equivariant maps, we deduce that the localization of mki at this maximal ideal is not 0. And so this, right, so this is the weight shifting thing. You exhibit that irregular form in something regular for all I in I or some I in I. And then we use our assumption, the star assumption, that local global compatibility holds for regular weights in the, okay, so maybe I should say regular weight and p-bounded for this strategy. And then we use star, which says that local global compatibility already holds for regular weight and p-bounded weights, regular and p-bounded weights, to conclude that our mod p representation is a point of xki. Okay. So this is one way to approach step 1. Yeah, okay.
Now, are you saying this weight shifting map is always injective?
No. I'm not saying that. You just want to make sure that f goes to something non-zero.
But like how f is like something not random in any case?
Yeah, I'll say something about it. I'm not done with this step. I'll explain what the weight shifting maps will be. But right, so you need to be careful. You have to find a map that makes sure that f doesn't go to something non-zero. Because f is something you are a priori starting with. And right. Yeah, that's a good point. Okay, so for this first step, okay. Great. Okay, so we use certain weight shifting operators. So a classic one is multiplication by partial Hase at tau, which comes from the Verschuebung map, but it gives us an injective map, Hecke equivariant injective map. So like this is, let me say, multiplication by partial Hase at tau. Right, so it gives us an injective map into a weight, into a modified weight. And what do we know about this weight? So k prime tau is going to be k tau minus 1. K prime Frobenius inverse tau will be k tau plus p, and the same at all other embeddings. So this will be k tau tilde for tau tilde, which is neither tau nor Frobenius inverse tau.
Do you mean k Frobenius inverse tau?
Yes, thank you. Thank you. That's right. Okay, so let's stare at this for a second. Let's say you have an irregular weight. So k prime Frobenius inverse tau is 1. You could apply mu tau, and that would increase it by p. So it will bring it up to p plus 1, which is good, which is still p bounded. But at the adjacent embedding, it will reduce it by 1. So it's quite possible that even though you improve the regularity situation here, you worsen it here. But then this is not so bad, because then you can apply mu tau again at this embedding, and you can keep going as much as you need to until you get everything p bounded and everything regular. Right? So the point is that mu tau is a great operator. So this is very good. It will produce, through successive applications if necessary, something regular and something that will follow, that will do this that we want, right? So this will eventually produce something regular and p bounded. There's another operator called the theta operator. Again, a classic one. This is a differential operator, and this is not necessarily injective, and that goes to Hee-Jung's comment. So it is not necessarily injective, but by changing level if necessary, you can configure it so that the image of f will be non-zero. So basically, I'll cheat and pretend it's injective, even though it certainly isn't injective.
So when you say changing level, you mean something like making f as a new form, something like that?
Yeah.
Oh.
Okay, so this, right. So what is k prime going to look like this time? So k prime tau will be k tau plus 1, and k prime Frobenius inverse tau will now be, again, k Frobenius inverse tau plus p, and nothing at the other embeddings. Okay, so, right, so the above one was very good. But now this, it can be good, but sometimes it will produce something not p-bounded, right? So because if this was already p, let's say Frobenius inverse tau was, this one was 1, you make it good, but if this one was already p, you make it bad. Or not bad, you make it not p-bounded. It's still regular, right? So what I'm trying to say is that, caution, theta will regularize, by which I mean it will k, but theta of k after whatever number of applications you're doing may not be p-bounded. And why is that bad? Well, it can pose problems with step 2. And essentially, what ends up happening is that on the Emerton-Gee stack, as long as a weight is p-bounded, the crystalline locus of mod p representations of that weight, it's an irreducible locus. And maybe I should have said that somewhere. Okay, let me say this here. Okay, no, actually, I'll just continue. So, so this will basically, if it's not p-bounded, then this locus will typically be reducible. And what's worse, it will contain the other good weight we had produced as an irreducible component. And what will happen then is, okay, very unfortunately, when you intersect theta k with mu k for step 2, this of course contains mu k, and it cannot be contained in xk. And the reason is that the more number of irregularities you introduce, the lower the dimension of the moduli stack, xk. So essentially, this ends up being lower dimensional, and this ends up being top dimensional. So essentially, the regular loci are exactly the irreducible components of this reduced Emerton-Gee stack. So this is top dimensional in X reduced. And this is some statement coming from dimensions of crystalline deformation rings due to Kissen. But essentially, this kind of argument will never work if your theta k becomes reducible while mu k is not reducible. What you want is that both of them are irreducible components of the same dimension, so that when you intersect it, and distinct, so that when you intersect them, you end up losing dimension, which is what you want to be contained in xk. This is not the only problem with non-p-bounded stuff, but at least this is the problem if you're already working with p-bounded stuff. Okay, so, right, so now let's see, where are we? Oh no, I have more boats. This is a bad idea. Okay, so hopefully I've convinced you that we have a problem, that we do not have enough weight-changing operators to execute the first strategy. Okay, so, right, so problem. Need more weight shifting operators. To attain step 1. Okay, where do we find them? So hint or clue. In my joint work with Levin, Borade, Hilado, okay, Lee, Levin, Savitt, and Viersema, if k tau is 1 for some tau, then we exhibit on the Emerton-Gee stack side an inclusion of xk into some xk prime, where this k prime satisfies k prime tau is now, again, k tau plus 1, but k prime Frobenius inverse composed with tau is now this interesting reflection. So p minus k Frobenius inverse composed tau plus 2, and nothing at the other embeddings. So so if k tau is 1, then this is no longer irregular. And this reflection will not produce an irregularity because our weights are bounded by p plus 1. So this suggests, so this is a purely local observation. So this suggests this could be a candidate for a third weight shifting operator if we could find its automorphic counterpart. So solution is, well, solution is basically ask George Boxer. But more precisely, this is what he told us. Okay. Oh no, okay, sorry. All right, so great. So there is work by Tian and Shao which builds on work on geometric Langlands by Helm, that if you start with, basically implies that if you start with the Hilbert modular variety, the special fiber of the Hilbert modular variety, and you restrict to the vanishing locus of this Husserl at tau, then this is in fact a P1 torsor over a lower dimensional special fiber of a lower dimensional quaternionic Shimura variety. Lower dimensional Shimura variety. And what you could do is you could look at, oh, I should give this k prime a name. So let's call this k prime, as we call it in our 8th author paper. Oh, I omitted my last name, sorry. Anyway. K prime equals nu tau of k. That's a definition of nu tau of k. Okay, so if you look at the push forward under this map, pi, of the restriction of f to x tau, then this lives inside the degree 0 cohomology of this y fp bar, the special fiber of a lower dimensional Shimura variety. And in particular, it lives in some automorphic bundle of some weight, which combinatorially exactly matches with the weights predicted by this one. Okay, that's very, very promising. The problem is we do not have local global compatibility for this lower dimensional Shimura variety, so we cannot immediately conclude that this implies that the Galois representation lives in this locus of weight nu tau k. Right? So once again, so if local global compatibility was true for y, we would be done. We would be done we would have shown that would imply that rho bar GFV lives in the locus x nu tau k, which would give us a step, which would help us fulfill step 1. So remember, in step 1, we wanted to produce more than one regular weight. We know that the weight mu is very good. Theta can sometimes be bad, so we want at least one other regular weight. And here, if local global compatibility held here, we knew it held here, then we could deduce that rho bar lives in x nu tau k. But, well, we don't know it's true. But we know that it is true in some generic range because of, again, Deding-Yang's ampleness results. So it's true in some generic weights. Only, and not, well, is known to be true. only in some generic weights on Y, again because of Yang and Delaunay-Lucy arguments. Great. So let me state our expected theorem 2. Expected theorem 2 is basically a solution to part 1, the step 1 of that proof strategy. So expected theorem 2 says that if F is, again, your usual eigenform, K, rho bar odd, the usual thing, rho bar, blah, 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 and you assume local global compatibility for p-bounded regular weights on the Hilbert modular variety. So our start condition on X, the Hilbert modular variety. Now, if K prime is a regular and p-bounded weight, produced by applying your favorite sequence of mu, theta, and nu, applying mu, theta, nu in any sequence, then rho bar, the restriction of rho bar to the decomposition group, lives inside the this mod p crystalline locus of weight K prime. Okay, so this is exactly answering step 1, where we are furthermore working with p-bounded weights. And that's good for step 2. I really wanted to, okay, maybe I'll say something about its proof very quickly. So okay, so by what I've already said, essentially the only interesting case is when K prime is nu of K, and mu and theta are already dealt with by the assumption star that local global compatibility already holds for p-bounded regular weights. So check for K prime equals mu K. So the point is that modify your Hecke eigenform as necessary by applying mu and or theta to F prime in such a way that the weight of now the push forward of F prime restricted to the vanishing locus of the Hase, this is now in the generic weight range, which is no longer necessarily p-bounded because we've applied theta on it, mu and theta on it on a regular weight on possibly regular places, so not necessarily p-bounded. Such that generic in the sense that Dedding's results tell us local global compatibility. Sorry, Dedding's, okay, so I shouldn't say it this way. So Dedding will imply that local global compatibility holds true in some generic weights, generic p-bounded weights. But essentially what he really gives us is lifting to characteristic 0. And now we are not in necessarily p-bounded case. So Dedding results will tell us that the Hecke eigensystem lifts to coherent cohomology in characteristic 0. But again, in some not p-bounded weight. So this is coherent cohomology. You could use the BGG complex to pass to étale cohomology. And then you can use maybe there are perhaps more than one way of doing this, but one way would be do Jackie-Langlands, to pass to some 0, 1-dimensional Shimura variety, apply some Savitt conjectures there. But you can basically deduce from this that your representation is going to occur in a union of some regular weights. So you can no longer guarantee, because of this outside of p-bounded nets condition, you can no longer guarantee that it lies in just one of these p-bounded loci, but you can guarantee that it lies in some union of p-bounded loci. Okay, so what now? Does it make sense? Essentially, our problem was that we were not able to lift to characteristic 0, so we couldn't do anything with this. But if you can change the weights enough by first applying mu or theta, then you can lift it to characteristic 0, and then you can do it. But in the process, you've changed the weight to something not p-bounded, and now the locus it lies on is no longer irreducible. So there's a problem. But in this case, remember that the locus obtained from applying mu was still very good. So we show that, and this is a really non-trivial step, but I'll just sort of write it trivially, but x mu k intersection with the union of all of these xkj's that can show up when you change the weight and then do this restriction to Goren Oort strata, this is in fact contained in xk. So this is a local computation now. Oh, xk, x nu tau k, yes, thank you. That's correct. So in other words, we've shown that because rho bar already certainly lives in the x mu k locus, and by this argument, it also lives in this union, we take intersection with every single component that can show up, and we show that it all lives inside x nu tau k. All right, so let me say something about step 2. So that deals with step 1. We've got enough crystalline loci, regular crystalline loci that our rho bar lives in. So for step 2, we compute scheme-theoretic intersections on the Emerton-Gee stack of all possible p-bounded regularizations of k p-bounded regularizations obtained by applying your favorite sequence of mu, theta, and nu. And we check that there exist at least 2 such regularizations. Oh, there exist at least 2 such regularizations, k1 and k2, such that our irregular locus is in fact the intersection, scheme-theoretic intersection, and not just at the level of points. It's a scheme-theoretic intersection of xk1, xk2. Right, so this is step 2. And let me make a very quick comment. So this is obviously an overkill. You do not need a scheme-theoretic description for step 2 to go through. You only need a description on points. On the other hand, this is good for the future. The second step is, the second comment I want to make is, I want to point out the work of Hanneke Wiersema, who has recently put out a paper on the archive. So she works in the setting, remark, Wiersema works in the setting where these k taus are between 1 and p. So she excludes the edge case p plus 1, where essentially this theta ended up being an issue. And although she can do some more, but essentially in the range where theta is still not an issue. And she produces certain very, very specific regularizations by applying mu and theta in a very particular order. And she shows that at the level of points, this statement holds true for her very specially and carefully, specially chosen weights K1 and K2 obtained by applying mu and theta. And certainly, this is absolutely enough to prove our theorem in the case k tau does not go to p plus 1. OK. So do I have any time left? Sorry, I've forgotten what you said.
I think you have maybe 2 more minutes.
OK, 2 more minutes. Sorry. OK, in 2 more minutes, let me say something about how to do step 2. OK, so the idea of proof of step 2 is that, so let L be any p bounded weight. Yes, sorry? Between 1 and p plus 1. So contrary, p plus 1 is certainly bigger than p, but the differences in Hodge state weights are bounded by p. Yes, thank you. P bounded weight. Then we have, sorry, I'll write abbreviations, Kalyani, Emerton-Gee, and Savitt, plus my joint work above, mentioned earlier. We show that if you have this locus of mod P representations living inside the reduced Emerton-Gee stack, then there exists a proper and scheme-theoretically dominant map from some stack, which I'll denote by CL. It's a certain closed substack of stacks of Broykissen modules, which can be described in terms of linear algebraic data. So there's a good handle on these. Okay. So now one can in fact use recent work of Lehung, Mézard, and Mora, and my joint work with Ben Savoy, to actually do a slight modification, to show that smooth locally, you have a diagram like so. You have a diagram. So this is XL. This embeds in X reduced. And there is some, because we are working smooth locally on some scheme charts, there is some auxiliary scheme, which maps properly or surjectively onto some, let's say, ZL, which lives inside X reduced. So this is a closed immersion. This is proper and scheme-theoretically dominant. This is proper and scheme-theoretically dominant. These are closed immersions. And this is incredibly explicit. This is wonderful as well. This is messy a little. This is horrible. And this is, well, basically impossible. OK, difficult, let's just say. OK, so what do we do then? Sorry. If I'm out of time, I'll just stop, and then I can, OK, well, maybe not. So, sorry. So, right, so the key construction to making this work is to show that construct a family of closed subschemes, or because it's smooth locally, so you're actually working with schemes, construct family of subschemes of the ZL, so closed subschemes Y of ZL, such that, let's call this map Q, such that if you look at Q inverse Y and you intersect it with this moduli stack, CL, then its scheme-theoretic image is actually Y intersection with ZL, or with XL. So some compatibility between pre-images and scheme-theoretic images for these closed subschemes, and you do this by comparison to some lower rank cases. And then sort of the point is that when you intersect K1 with K2, you show that it actually lives inside, well, ZK1 and ZK2, which actually lives inside some suitable Y of this form, which means that which means that you can, which means that it is contained in the image of Q inverse Y intersection CL. And now you have to compare this strategically chosen closed subscheme of the CL with CK1 and CK2. And there are some diagrams and you have to construct some sections, but basically you can do this. And that's that. I'll stop here, and I apologize for going over.
Thank you. Are there any questions?
Yes.
If I kind of give myself, say, Burmazar or something, can I kind of guess what countertargets I have to work out? Or is it like how? I mean, is it like these different intersections and things like?
I don't think the Breuil-Mazard conjecture helps in.
I mean, that's a figure. I mean, that's like figure. I just curious to figure out what you're supposed to do.
I don't know how it would help because we're working with irregular loci, and
okay.
Oh, I mean, so this entire picture works for irregular loci as well. In fact, you need that because you want to compare the intersection of the regular loci and show that it lives inside the irregular locus. But if you wanted to work with non-p-bounded weights and you gave me the Breuil-Mazard conjecture, then maybe a lot could be said.
Okay.
But, sorry.
That's okay.
Yes.
When you express this xk as like xk1 intersection xk2,
yeah.
So first, is it always suffice to just take some two special k1 and k2 to their intersection becoming this xk?
So we can characterize exactly which pairs will suffice and which will not suffice. So I didn't want to introduce more terminology, but basically we call them divergent regularizations. And they have to be sufficiently apart in a way that you can actually intersect them to get xk.
And when you talk about this scheme-theoretic intersection, do you consider possibly non-reduced structure, or?
We consider everything. So the scheme-theoretic intersections, sometimes they're irreducible. I haven't seen non-reduced intersections so far, but I've only explicitly computed when there are two irreducible components.
Oh, but what about like nilpotents?
There are no nilpotents. So I'm saying that okay, so let me say that in the case that the intersection is irreducible, it's always reduced. In the case that there are two components, it is still always reduced. I'm not sure what happens if there are more than one irreducible components in the intersection. I haven't checked that, but one can explicitly determine anything. And I should say that even though I'm working with certain specific regularizations, this technique can actually, I think, tell you basically about pretty much any intersection you want to know. Within some limits, yes.
Weight shifting operator, maybe it's naive, but like you have theta tau from like mk1 to mk2.
That's right.
On both sides.
So you mean which operators I'm applying?
It doesn't exist here, but it's on the hidden blackboard.
Oh, sorry.
Not much.
Oh no, okay. Sorry about that.
I got this theta tau. So on spectral side, you also have this inclusion of K1, K2.
That's right. Yes, so you do have an inclusion of chi k into chi k prime correspondingly. So we have inclusions. Right, so I should say that in fact on the spectral side you do have inclusion of xk into x mu k, x theta k, and x mu k, where I'm not indicating the subscript because you can apply multiple ones if you like, and successively if you like, and so on and so forth, as long as they produce something p-bounded.
I just want to ask whether there's relation between these two maps, like under.
Between this and this? No.
Between this
and this and this? I mean, this corresponds. I mean, the hope is that it should correspond. Like if you believe, essentially Langlands would tell you that if this eigenform also, if this Hecke eigensystem also shows up in weight k prime and local global compatibility holds true, or forget about Langlands, but essentially, well, not forget about Langlands, but I mean like local global, the statement of local global compatibility that we are working with, that implies that anything here should show up here, and anything here should show up here. And so if local global compatibility is true, then this inclusion should hold true. Or, well, if a stronger form of local global compatibility is true, then this should hold true. Does that answer? Sorry, maybe I was very confusing just now.
I mean, maybe one can say that in the end there'll be a version of categorical Langlands where you kind of convert these modular forms into coherent sheaves too, and then this will be some statement about supports, and there'll be, I mean, that MK prime will just be some kind of, probably some surjection of coherent sheaves on the stack, and then you'll take supports and this will pop out. So which is a fancy way of saying what you said.
Right, well, thank you. Yes.
Thanks.
Okay. So, any more